Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton's third law, the third and final of Newton's three laws in motion, three laws of motion. And it's a fundamental law of mechanics, so that seems like a pretty big idea to me. So let's dig in. So, the most succinct statement I know of Newton's third law is this: forces come in pairs. What do I mean by that? Well, this picture, which I copied from my edition of the Wolfson textbook, sort of illustrates the basic idea. So suppose we have two objects, your hand, which we'll call object A, and your copy of the Wolfson textbook, which we'll call object B. And then we'll define a notation here. We'll say that when we write F sub AB, by definition, what we mean is that this is the force exerted by object A on object B. So F sub AB in this example, A is your hand, B is the book. This is F sub AB is the force exerted by your hand on the book. And in this picture, we see that F sub AB points to the right. You're pushing to the right on the book. Similarly, when we write F sub BA, by definition, what we mean is the force exerted by B on A. So in this example, F sub BA is the force that the book exerts on your hand. And what the second law, what the third law says is when we say that forces come in pairs, we can write it succinctly with the following statement: F sub AB is equal to minus F sub BA. So what the third law says is that if your hand is exerting a force on the book to the right, then the book must exert a force of equal magnitude and opposite direction on your hand. That's what this minus sign here means. If the two vectors are equal except for a minus sign, what that means is that their magnitudes are equal, but their directions are opposite. So this equation here is sort of the succinct mathematical statement of the third law, and this statement that forces come in pairs is a shorthand way of saying this. If A is exerting a force on B, then B must be exerting a force of equal magnitude but opposite direction on A. And if you really want to understand the third law, I suggest you take up prayer. And I mean that in the following sense: take your two hands and hold them together in this prayerful pose and have your hands push on each other. And with the third law, you should feel if your left hand is pushing on your right hand, you'll also feel a force from your right hand pushing on your left hand, and you should convince yourself that these forces point in opposite directions, but it's plausible that they have the same magnitude. And the third law is often invoked to explain how rockets work. And this is another picture that I took from your Wolfson text. And the argument is that the way a rocket works, as you probably know, is that you shoot hot gases out of the back of the rocket, out of the rocket's nozzle. And if the gases are shooting to the left, the rocket's going to go to the right. And now the third law provides a sort of deeper explanation as to why if the gases are being expelled out of the back of the rocket, the rocket must have exerted in some way a force to accelerate these gases out the back. So the rocket is exerting a force pointing towards the rear of the rocket on the gases. And then the third law says that therefore the gases must be exerting a force on the rocket that points towards the front of the rocket, and the rocket, therefore, is going to move in this direction. Now, the next question you might ask is, well, why does F sub A B equals minus F sub BA? That is, why is the third law true? What makes this happen? One way of answering that question is I don't have to answer. It's a law. And fundamental laws of nature, we really can't answer the why question. The way physicists look at the world is we try to identify these fundamental laws and then try to understand what the consequences of those are, of those laws are. But at some point, you really can't answer the question of why a fundamental law is true. Now, having said that, in the case of the third law, there is some deeper truth or law that we can point to. And we've already mentioned in a previous episode of What's the Big Idea, Newton's law of gravity. And the law of gravity, and we'll talk a lot about the law of gravity, but as we've already mentioned, the law of gravity stipulates that there's a mutual attraction between any two masses. And the word mutual is pretty key. What the law of gravity says is that if you have a mass one and a mass two, then mass two will exert, in this example, a rightward going force on mass number one, and mass number one will exert a leftward going force on mass number two. And built into the law of gravity is really the third law, because these forces point in opposite directions and have equal magnitudes according to the law of gravity. So the law of gravity sort of requires that in this case, that F sub 2, 1 is equal to minus F sub 1, 2. And if you take Physics 108, you'll study, which has to do with electricity and magnetism, electrical forces. You will find out that when you have charged particles, the structure of the fundamental law, Coulomb's law, is very similar in spirit to the law of gravity. Again, it involves this mutual interaction in which the third law is sort of built in. If you have two charged particles, then it'll turns out to be true that F sub 2, 1 will always be equal to minus F sub 1, 2. Now, the difference with gravity between Coulomb's law and gravity is that the forces can either be attractive or repulsive, depending upon whether the masses have opposite or the same, whether the charges have the same sign or opposite signs. That's a detail. The point I wanted to make is that in both these fundamental laws of nature, the law of gravity and Coulomb's law, the sort of mutual interaction builds in the third law. So you could say ultimately the third law is sort of a consequence of these perhaps more fundamental laws, the law of gravity and Coulomb's law. Okay, so to test your understanding, maybe let's consider this convince your neighbor problem. I have my Toyota Prius parked in the garage outside my house, and right now the Toyota Prius is not moving. It's at rest, and in fact, it's been at rest for many months now due to the pandemic. But that's another story. The question in hand is, just given that my Prius is at rest, which of the following statements is true? Uh, um, the question is, we can conclude that the downward gravitational pull of the Earth on the car and the upward contact force of the ground on it, the car, are equal and opposite because of the following. Is it a consequence of the fact that the two forces form a third law interaction pair? Is it true because the net force on the car is zero? Or is neither of these statements true, or are both of them true? That's the question at hand. And let's pause. I want you to press pause on the video and think about this. And we will give you a little while to think. And then when you're ready when you've settled on an answer, press play, and we'll see if your answer agrees with mine. See you soon. Okay, we're back. Well, before I give you my answer, let me give you some reasoning here. I want to write down the statement that's written here, I want to write it down in terms of the notation that we just developed. So we conclude that the downward gravitational pull of the Earth on the car. So I want to write that in terms of a force with two subscripts. So the downward gravitational, it's the force of gravity on the car. And so the convention that we've adopted is that with these subscripts, the first subscript that refers to the thing, it's the force by the first thing on the second thing. So the downward gravitational force pull of the Earth on the car, I'm going to represent that by F sub gravity on the car, F sub grav comma car. And that I'll indicate the direction of that by drawing a downward arrow. The force that gravity exerts on the car is clearly pointing down. Then the second thing that's mentioned in this sentence is the upward, quote, contact force of the ground on it, on the car. So in our notation here, the force of the ground on the car, I'm going to write it as F sub ground comma car. It's the force by the ground on the car. And that clearly points in the upward direction. Okay, so far I think everything I've said is true. Now, the question is statement number one here a true statement? Do these two forces form a third law interaction pair? What do you think? The answer is no. Why no? Well, remember the way we wrote the third law in terms of our notation. To recognize a third law pair, the characteristic would be, in terms of this notation, the two subscripts have got to be the same except their order is reversed. And here we see that both of these forces act on the car. So they are not a third law pair. In fact, the right way to analyze what's going on in this problem is in terms of the second law. So the second law, N2, remember, says that the acceleration of an object is equal to the net force acting on that object divided by the mass of that object. And in this case, the object that we want to apply the second law to is my car. So the acceleration of my car depends on the net force acting on the car divided by the mass of the car. And because my car is at rest in this problem, we know that the acceleration of the car is zero. And therefore, by virtue of the second law, it must follow that the net force that acts on the object must be zero. Now, what forces contribute to the net force on the car? Well, they're the two forces that we've identified here. Both of these forces act on the car, but they are equal and opposite in direction, and that really is responsible for the fact that the car is not moving. So statement number true here is a true statement. Statement number one is a false statement. So the correct answer to this problem is 2. And now I'm going to leave you with a puzzler, something to puzzle over. We have a very smart horse here who refuses to try to do her work by pulling the car because this horse has taken Physics 107 and she thinks she understands Newton's third law, and she says, well, I can't move the car to the right, since if I pull on the car to the right, the the car will exert an equal and opposite force on me to the left, and therefore, how can I move to the right if there's a leftward going force on me? So my question to you is, what do you say to this seemingly wise horse? So that's about it for now. That's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.